call, isn't it? It is 4 minutes fast, slow.
4 minutes slow.
Yeah, cool. All right, well, it is my pleasure, as always, to introduce Bailey Murphy, who is here to give the public seminar to her Ph.D. defense, which is happening later today. And what you'll get to hear about is a collection of work that really is pushing the boundaries of how we think about forests in the Earth system, and particularly how we manage our forests in the Earth system. And it's been quite a delight to see this project kind of come to fruition over the years. It was with some fits and starts for sure, and with some interesting tangents on different aspects of this project, but I think we have what you'll hear today is a real treat about what's coming together. So by way of introduction, Bailey joined my lab in 2018 of the fall, and she did both her master's and PhD underneath me. But I should bring out that she joined my lab already as a somewhat seasoned researcher, having done a number of projects before joining. And in fact, the reason that we even connected was because one of her former mentors at the USDA, Claire Phillips, who might be watching on the live stream, wrote me an email on the blue saying, I have this technician who's been working with me on biochar and studying lab incubations of soils and field work, who is fantastic, and you must recruit her. And that's, I often get the emails, but not one so direct, so it seemed intrigued. And Bailey visited in early 2018 into winter, and at that time I had another colleague visiting at the time, and so the three of us went out for drinks after the day was done. And at the end of that day, I was talking to my colleague April, and she just said 2 words to me: hire her. That's it. And that was one of the best decisions I've ever made. Bailey has been working diligently. In her application essay, I remember that she wrote something very specific that was, I think, a theme in much of her work and much of her education, which is that now more than ever, it is an essential skill that scientists are be able to communicate and work with others. And I think the project, as you'll see here, which required working with foresters and satellite remote sensing folks and ecosystem modelers and social scientists and demographers, understanding how foresters work, really requires strong communication skills across multiple disciplines, and that's something that we're going to miss having here. So prior to working with Claire, Bailey got her undergraduate degree at Oregon State, and she's had done some field work out there with a colleague of mine, Christoph Thomas, who was a micrometeorologist, and so she had already been exposed to flux towers in that world, doing soil respiration measurements in the field. She then worked with postgraduate with Claire Phillips at the USDA, working with lab incubations for biochar. She later then kept moving. So she grew up in Alaska and then just started moving south and then started moving east to Bozeman, Montana, where she worked in a plant pathology lab working on agricultural management of pests using a combination of lab and field trials. And then eventually showed up here. We also had a couple other detours as well, teaching English abroad, right, in Korea. A few other things. And then since her time at AOS, her master's thesis was focused on data assimilation in one of the models that then she ends up using for the PhD, as you'll hear today. And that was a really exciting work. She's published several papers coming out of her work to date, I think about 4, with another several more in the pipeline. And she's also been very active in our department, active with the Graduate Student Association as our facilitator. She was a co-founder of our very successful AOS mentoring program, which pairs graduate students with undergraduates, and that's been a real nice addition to our department. And starting in a month or so, after she successfully defends and moves on, she will be starting a position as a research associate at the Department of Energy Oak Ridge National Lab, working on a project in the Arctic, and we'll be hearing hopefully more about that in a few years. She'll be joining actually a former PhD student of mine, Sven Sullman, who's here visiting town, who is also at Oak Ridge and will be colleagues, boss, some relationship, but it'll be exciting to see. So I think we now have the Scilab Southeast growing there. And then there are snacks in the back, thanks to Bailey's family for bringing some additional food. So please wander over there and grab something. And with that, I'll turn it over to you. Thanks, Bailey.
Okay. Can everybody hear me? Yeah, that's on. Okay. Thank you all for being here today. Thank you, Walker, for that super nice introduction. I won't reread this giant title because it's an absolute mouthful, but today I'm excited to share some of what I've been up to for the past 3 years. We'll talk about carbon, forest management, and how climate change kind of complicates everything. Okay, so the terrestrial biosphere takes up a lot of carbon, and forest ecosystems are the largest terrestrial carbon sink on Earth. And this carbon is continuously cycled among the atmosphere and ecosystem carbon pools. So things like above and below ground biomass, dead wood, litter, and soil. And the cycling is driven by different biogeochemical processes in forests, things like photosynthesis, respiration, natural disturbances like fire and pest outbreaks, and anthropogenic activities like management and land use change. And forests store about 45% of the terrestrial carbon. They contribute about 50% of the net primary production, and they take up about 19% of the total carbon that's released each year through fossil fuel emissions and land use change. And this carbon sequestration and storage in biomass really attenuates global warming by helping to reduce atmospheric CO2 concentrations. And forests also provide really important climate feedbacks. So the land surface interacts with the atmosphere through these complex physical, chemical, and biological processes that can have a really profound impact on climate. And they can either amplify or dampen the effects of climate change. So for example, early work by Joel Charney in 1975 demonstrated the existence of biogeophysical feedbacks between deserts and the atmosphere. And he drew connections to the global implications of reduced vegetative cover in the Sahara. So Charney showed that deserts actually enhance their own dryness through high albedo, which contributes to a net loss of radiative heat. And this induces circulation to try and maintain thermal equilibrium that ultimately increase their own aridity. And forests really help sustain the hydrologic cycle through evapotranspiration. So this cools the climate through feedbacks with clouds and precipitation. And tropical forests in particular maintain high rates of evapotranspiration, and this decreases surface air temperatures and increases precipitation compared with pasture land. So work by Von Rando et al. In 2004 showed that large-scale conversion of forests to pasture land in places like the Amazon has resulted in warmer, drier climate. But on the flip side of this, high albedo, or the low surface albedo of boreal forests compared to places where there's an absence of trees during the snow season actually amplifies warming, so this acts as a positive feedback. And in addition to carbon storage and these complementary climate feedbacks, forests also provide a wealth of economic benefits and other ecosystem services like wood products, water regulation, and cultural and recreational opportunities. So improved management of forests has been recognized as a relatively cost-effective nature-based climate solution, where a nature-based climate solution is something that manipulates natural systems through management to try and increase carbon sequestration. And when you pair this with emissions reductions, it can help mitigate the effects of climate change. And nature-based climate solutions have the potential to sequester up to 1.2 petagrams of CO2 equivalent per year in the United States alone. So this is about 21% of net annual emissions, while also supporting a range of environmental and social co-benefits. And furthermore, nature-based climate solutions such as forest management could potentially be designed to increase resilience to climate change, like future climate change impacts. So things like increasing temperatures, increased storm severity, or enhanced vulnerability to pest and pathogen outbreaks. And forests have really been heralded as kind of this key climate solution by everything from the Paris Climate Agreement to startups promoting forestry-related carbon offsets. So in 2021 alone, the value of total transactions in global voluntary carbon markets for forestry and land use change related solutions was estimated at over $1.3 billion. And this represents a quadrupling of the value in 2020. However, and this is a very big however, forest capacity to uptake and store carbon is influenced by a range of socioeconomic and biophysical factors. So when we manage a forest, we fundamentally alter the physical structure of the forest. And this means we also change how the forest performs various functions and how the land surface and the atmosphere interact. But some really key gaps remain in our understanding of how management impacts processes that control rates and variability of carbon uptake, as well as how these vary across time and space. And our basic understanding of carbon flux and stock dynamics following disturbance is also pretty limited, particularly with respect to ongoing disturbances. And all of these unknowns contribute predictive uncertainty, and they make it really hard to design robust and scalable climate mitigation strategies. Additionally, the response of the terrestrial biosphere to changes in climate remains one of the largest sources of uncertainty in climate predictions. And so this makes it really hard to accurately predict the future of carbon source and sink magnitudes. So we know that forests and how we use them provide really important climate feedbacks and forcings, and we know that climate change can adversely affect some of these ecosystem functions, but we don't really have a firm grasp on how climate might interact with management across long timescales, and what this might mean for feedbacks with the Earth system. So if we want to be able to reduce some of this predictive uncertainty regarding the future of the terrestrial carbon cycle and be able to design robust mitigation strategies, we really need to improve our understanding of how human management impacts forest function across spatial and temporal scales. But scale is also a challenge. So one of the key challenges in addressing these unknowns is that forest management, structure, function, and climate are all controlled by different processes, and all of these processes involve different scale-dependent emergent factors that affect those processes, and they're regulated by different Earth system feedbacks that operate at different spatial scales. And all of these dimensions kind of change how resources are spatially distributed. They change forest resilience to disturbance, the net exchange of carbon and water, and overall carbon storage estimates. So coupling experiments with models as well as multi-factor manipulations is one way to try and address these challenges of scale. So observational data from field campaigns and experimental manipulations can provide opportunities for really detailed investigation of some of these relationships at the leaf to landscape level, but they're often constrained temporally. So models are kind of then this particularly useful tool that we can use to investigate these trends across long time scales, where these observational studies are more limited. And using ensemble analysis under variable conditions allows us to kind of address some of these big what-ifs that were mentioned previously. So advancing understanding of terrestrial ecosystems and their role in the Earth system requires a balance between observations, theory, process parameterizations, and modeling studies. And so the work that I'll present today incorporates both observational analysis and process-based modeling studies to try and to represent kind of a macrosystems approach towards understanding these interactions between management, structure, function, and climate change. And when I say macrosystems approach, what I mean is studying ecological dynamics and feedbacks at multiple interacting spatial and temporal scales. So here we'll expand from the stand to the regional scale and across seasonal to multi-decadal timescales. So in pursuit of this, 3 overarching questions were asked. Question 1, what is the mechanistic relationship between forest structure and function? Question 2, which is the primary driver of future variability in forest function? Is it management or is it climate change? And question 3, how does management impact the stability of forest function in the face of climate change? So we'll start by zooming in to the site scale to evaluate these mechanistic relationships between forest structure and function. And when I say forest structure, I'm referring to the physical arrangement of the forest. So things like tree height and size, distributions of variability, the degree of canopy closure, etc. And when I say function, I'm referring to things like carbon, water, and energy cycling, as these tend to define land-atmosphere exchange. So recent work has shown that structurally complex forests often have higher levels of productivity, and this is potentially because of their ability to optimize available resources and assimilate carbon more effectively. And this indicates that there could be really strong links between forest canopy complexity and ecosystem functions. But both the mechanisms underlying these links and how they might change over space remains unclear. And why does this matter? So if we want to explore links between management, function, and climate change, examining structure is one way to do that, because management directly alters forest structure in a way that we can tangibly measure. So in recent years, the availability of airborne and terrestrial LiDAR has really expanded our ability to explore and quantify forest structure. But now we're in sort of this weird position where we have all of this data on all of these features of forest structure, but we don't really know which metrics are the most important in terms of scaling to ecosystem scale and beyond, or which are carrying redundant information, or what the spatial scales of importance are. So one approach to addressing this is by pairing high-frequency measurements of land-atmosphere exchange with high-resolution measurements of canopy complexity that are taken within the same spatial domain, where we can kind of control a little bit for the variability in climate, forest functional types, and soil fertility and other adaptive factors. So the ChiSo Field Campaign, which stands for Schwamigan Heterogeneous Ecosystem Energy Balance Study enabled by a high-density, extensive array of detectors, provided a great opportunity to do this. So ChiSo 19 was an intensive field campaign that spanned from June to October of 2019 up in northern Wisconsin, and it involved 20 flux towers located within this 10 by 10 kilometer study domain shown by the black box. And in addition to these flux towers, we had ground sampling of vegetation, airborne measurements, large eddy simulation, and a whole lot else. And the primary goal of this project was to really understand the role of boundary layer responses to scales of spatial heterogeneity in land-atmosphere exchanges of heat and water. And so this map depicts the ChiSo 19 study domain, and each of these red dots shows the location of a flux tower, like the one shown in this picture. So 9 forested sites were selected to measure forest composition using drone-based LiDAR, and our sites spanned a range of stand types and disturbance histories and successional stages. The youngest site was on average 8 years, and the oldest was 151. And for each site, 20 unique metrics describing the structure of the forest were calculated at 5 different spatial resolutions, so ranging from 0.25 to 50 meters. And we paired any covariance measurements of carbon and water exchange from the same 9 sites with these LiDAR measurements to establish which structural metrics were the strongest drivers of productivity and examine scale dependence of those relationships. So we use structural equation modeling, or SEM, specifically path analysis, to test potential mediators of that relationship. So light and water use efficiency were tested as potential mediators through comparison of reduced and saturated model designs. So in the reduced model design, complexity metrics are only able to impact productivity by acting through resource use efficiency. Whereas in the saturated model design, it allows for that same pathway, but complexity metrics can also just directly impact productivity. And in terms of the structure-function relationship, we found that a positive mechanistic relationship existed between complexity and productivity, and that this relationship was mediated by the effective acquisition and assimilation of, or was mediated by light and water resources. And that resource use efficiency in general was enhanced by increasing structural complexity. We also found that vertical heterogeneity metrics were the most influential in predicting productivity. And lastly, which complexity metrics were included in the relationship, as well as driver strength, was dependent on resolution. But the persistent superior performance of that reduced SEM suggests that even though metric values changed slightly, the existence of mediation effects was not scale dependent. Okay, so next, we'll expand in scope by bringing in a process-based model. And this allows us to really compare multi-decadal simulations of force dynamics in response to management. And we're going to do this in 2 US regions, and using simulations conducted under alternate radiative forcing scenarios, which really allows us to capture those climate change impacts. So when I say model, that can mean anything from y equals mx plus b to like millions of lines of code. So I'll give a little bit of context before I jump into the experimental design. So climate depends on the whole Earth system, and it evolves in response to these complex interactions between the sun, the biosphere, cryosphere, geosphere, and atmosphere. And so all of these things have to be represented in Earth system models. And they're typically represented as component models that interact through some sort of flux coupler. But here, we're really just interested in what's going on with the land surface, and particularly how vegetation is responding to changes in management and climate. So we're just going to focus in on this land surface model side of things. And so because management primarily affects function by altering forest structure and vegetation dynamics, we need a special class of model that's able to capture that. So what's known as a vegetation dynamics model. So for this work, we utilize the ecosystem demography model version 2 or ED2. And this is a size and age structured vegetation dynamics model. It includes ecophysiology and biogeochemistry submodels. And it's capable of tracking the dynamics of these really fine scale ecosystem structure and function changes and linking short-term fluxes to long-term shifts in dynamics. And ED simulates competition, demography, and community composition using cohorts rather than individual trees. So it makes it less computationally expensive than other options, where a cohort is a group of trees that has similar age and size dynamics and are within the same plant functional type. And ED requires sub-daily meteorological data as well as soils and stand level inventory data, and it outputs a range of variables related to ecosystem structure, so things like growth, mortality, and above ground biomass, as well as fluxes, so things like evapotranspiration and gross primary productivity. And these ecosystem descriptors, such as carbon pool magnitudes and fluxes, are emergent properties that result from simulated competition for resources between plant types that have differing abilities to survive. And ED is also hierarchically organized, so this kind of like hierarchical spatial organization of the model really facilitates capturing heterogeneity and being able to scale these relationships. So water, energy, and carbon dynamics get resolved separately for each patch, which means that the response to disturbance can be explicitly tracked. And we chose to conduct model simulations at National Ecological Observatory Network, or NEON sites, in 2 regions, the Great Lakes region and the southeastern US. And we use core terrestrial NEON sites because they're representative of their respective ecoclimatic domains. And NEON is this continental scale observation network. They have 81 field sites across the US. It's slated to run for 30 plus years. And they collect just all sorts of data on everything from energy fluxes to mosquito populations to try and capture how ecosystems are changing and how climate is changing. So we use NEON data on tree species and structure as well as soil properties to initialize our model runs. And we also use downscaled global climate model, or GCM, data from a suite of 10 CMIP5 models to drive the meteorology. And this allowed us to simulate climate conditions under two alternate future radiative forcing scenarios, RCP 4.5 and RCP 8.5, as well as be able to make predictions from the year 2006 out to 2100. And so here, RCP 4.5 represents an intermediate emissions scenario, and RCP 8.5 represents a high emissions scenario, so we can think of it as more severe climate change impacts. And within Ed2, we implemented 4 different management types, and these represent a range of practices, and they really reflect varying balances between ecosystem goods and services, such as biodiversity support, wood products, and hydrologic regulation. And we used regionally specific management model parameters that were derived from interviews with over 100 forest management experts across the US. So broadly speaking, preservation forestry seeks to maintain sort of this baseline state. And in the context of these simulations, it's akin to like a no management scenario. So this is basically just leave it as it is. Passive management lacks any active management other than occasional harvest. Ecological management uses ecological principles to balance wood production with other ecosystem services. And production forestry represents our most intensive management practice, and you're basically just trying to maximize wood and pulp production. And so management is prescribed in Ed by altering harvest parameters such as the timing, frequency, and spatial extent of harvest, as well as the plant functional type, age, and size groups that get targeted for that removal. So what does the future hold? In terms of climate, the Great Lakes region is projected to see steadily increasing temperatures that outpace precipitation increases. So we'll see an increase in vapor pressure deficit, whereas the southeast is basically just going to get really, really wet. And so in the figure here, our columns correspond to regions. Box plots are colored by management type, and shade represents RCP scenario. So the darker shade is RCP 8.5. Values are shown for the start and the end of the century. And our rows represent a few key variables related to carbon storage. So on the top, we have above ground biomass. In the middle, we have gross primary productivity. And at the bottom, we have net ecosystem exchange, which is basically the net carbon balance. And so what we see is that the Great Lakes region tends to have larger soil carbon stores and higher productivity than the southeast, but it's ultimately less of a net carbon sink by the end of the century compared to the southeast. And here I should point out that more negative is more of a carbon sink. And so this is really because respiration increases outpace productivity gains in the Great Lakes region, and this led to a transition from a net carbon sink to a slight source under the more severe climate change scenario. And total carbon storage decreased in the Great Lakes under the more severe climate change scenario, especially soil carbon. And this indicates that the observed increases in respiration that we saw were likely due to accelerated decomposition. And carbon storage in above ground biomass also decreased over time in the Great Lakes, and this was really the result of increased mortality. In the southeast, however, the region remained a consistent net sink of carbon that increased in magnitude over time for most management types. And productivity and soil carbon also increased under the more severe climate change scenario in the southeast. And mortality did increase slightly, but ultimately trees overall got larger and took out more carbon. So climate is changing. How is function changing, and what's driving it? So we've now made it to our second research question, which is the primary driver of future variability in force function, management, or climate change. So our first step was to reduce data dimensionality and determine the dominant axes of future variability in force function. And we did this using principal component analysis, or PCA. And we went this route because we're more interested in how ecosystems respond as a whole to changes in anthropogenic drivers in climate than in how any one individual variable is changing. So we started with a set of variables representing carbon and water cycling, as well as resource use efficiency. And annual growing season averages were calculated, and region, RCP scenario, and management type were retained as supplementary categorical variables. And significance testing was then performed to determine both the ideal number of components to retain, to try and minimize redundancy but avoid information loss. And the significance of loadings was also tested using a simple fixed threshold approach as well as a more rigorous bootstrap eigenvector method. And what we found was that the first two principal components were statistically significant and captured about 83% of the variability in future function across all region, climate, and management types. So this figure here shows individual variable contributions to each principal component, and green circles indicate that a loading is statistically significant. So our first axis of function, PC1, represents the majority of the observed variability, and it's primarily defined by variables related to water exchange, respiration, and productivity. And our second axis of variability, PC2, is really dominated by net ecosystem exchange, and this is a variable that describes the balance of carbon uptake between the atmosphere and the land surface. Net conductance to water vapor and CO2, as well as light and carbon use efficiency are also important for this dimension. So these two figures here show individual data points plotted on the first two principal components. The figure on the left is colored by climate change scenario, and the figure on the right is colored by management type. And you might notice a distinct clustering of points, which corresponds to geographic region. So the yellow is southeast, and the green is Great Lakes. And so we found that management impacts on function and interactions between management and climate were really regionally dependent. And regional differences in average PC values were the most distinct for the first axis of functional variability, where these group mean values were always statistically different between the two regions, regardless of RCP or management type. So next we wanted to evaluate the strength of drivers at the regional scale. So we used generalized additive modeling, or GAM, fit separately for each region to try and determine the degree of variance in PC values that could be attributed to management type, climate change scenario, or interactive effects between the two at the regional scale. And year was also included as a smooth predictor to account for temporal autocorrelation, and we tested the significance of differences across groups. What we found was that management was more important than climate change scenario at the regional scale. So in the figure here, columns correspond to management types, rows are geographic regions, and colors represent RCP scenario. And so these polygons here depict the relative balance between different ecosystem functions, between management types within each region. So each functional variable is grouped by region and RCP scenario and scaled from 0 to 1. And we saw that the effect of management on ecosystem function was 1.2 to 16.3 times greater than the effect of climate change scenario. However, the effect of management was greater in the southeast, where these functional differences between management types were more pronounced. And interaction effects between management and climate were only significant in the southeast. So this tells us because the effects and interactions between management, function, and climate depend on geographic location, This means that the same management strategy will have really different climate mitigation potential depending on where it's applied. So kind of this forestry-related climate solutions is not a one-size-fits-all thing, and it really has to be evaluated at the regional scale. So next, we wanted to test whether this dominance of management over climate held true at broader spatial scales. So we used random forests to build a predictive model and identify and rank the importance of different structural and climate drivers of function. And this really allowed for potential nonlinear interactions between variables. So random forest was conducted with individual principal components as the response, and forest structure and climate metrics from these simulations as the independent variables. And we used data from both regions combined. So data was divided for training and testing using a 10-fold cross-validation approach. And so this is a resampling method that splits the data into K groups to train and test each model on multiple iterations. And in and out of sample R-squared values were computed for each possible formulation to test performance. And for a predictive model to be considered causal, it has to be invariant across different data environments. And so two distinct data environments, or subsets of the full data, were defined for testing the invariance of all these possible model formulations, where an invariant model is one that is stable in its formulation across different environments, regardless of heterogeneity in the data. So here we use geographic regions as our different data environments, and this is because each data point could only be assigned to one data environment, and differences like latitudinal differences in forest type and climate and management practices, as well as disturbance histories, could introduce enough heterogeneity into the predictor variables. And I also tested for conditional independence among these random predictor variables and computed a p-value for invariance for each combination of response and predictor. So after determining the best fit random forest model, driver importance was then assessed for both individual variables as well as groups of variables. And so group membership was based on whether a variable represented structural factors or climate factors, where structure is kind of our proxy for management. And individual variable importance was assessed using a permutation-based variable importance measure. So this is done by calculating the change in model predictive error before and after permuting variable values. So this is basically like a sensitivity measure. It tells you how sensitive model accuracy is to small changes in your predictors. And predictive performance of grouped driver variables was estimated for each PC using a five-fold cross-validation and calculating an R-squared value for each group and PC combination. So we found that the best fit predictive model was invariant across the two data environments, so meaning that this best fit model was not regionally dependent, but the majority of possible model formulations were invariant. So this means that we can't say that the full model is in fact causal, we can only say it's a plausible causal model. So in this figure here, the x-axis represents the percent increase in error in response to perturbation of individual variables. So a higher value means that the model is more sensitive to changes in that variable. And the first two rows correspond to PC1, and the bottom two rows correspond to PC2. And individual variables are included, that were included in the predictive model, are grouped on the y-axis based on whether they were related to structure or climate, with climate variables in purple and structure in green. And so we found that the dominance of climate versus structural variables as drivers of function really depended on functional axis. And these grouped climate variables were stronger predictors of PC1, so this was our water exchange, respiration, and productivity axis, whereas grouped structural variables were stronger drivers of PC2, so our net ecosystem exchange, and resource use efficiency axis. And this indicates that when we're expanding to the subcontinental scale, to incorporate data across multiple regions, these differences in climate really become critical. But the importance of climate over structure for PC1 was pretty narrow in terms of looking at the grouped predictors. And so this suggests that their effects are likely not independent of one another. And this has been supported by observational studies showing that interactions between climate and forest structure and demography kind of explain some of these forest functional responses better than any of those factors alone does. And that these functional responses to climate, especially things like changes in precipitation, are often mediated by competition and structural factors such as tree size, which are directly impacted by management. So moving on to our final section, looking at functional stability. So our final research question was, how does management impact the stability of forest function in the face of climate change? So broadly speaking, functional stability refers to the ability of an ecosystem to withstand and functionally recover from perturbation. And climate conditions really affect how forests respond to disturbance, but there's a lot we don't know about how functional stability will respond to perturbations, or how those will shift in response to climate change. Although recent evidence suggests that stability is declining for many forest types, and that this is potentially in response to increasing intensity and variability in large-scale climate drivers. So as forests become less stable, the likelihood of large-scale mortality in response to disturbance increases. And this means that a significant portion of the stored carbon could be released, which basically nullifies your mitigation efforts. So this was shown by a study by Wu et al. In 2023, and they found that a large percentage of carbon offset projects in the western US are basically at high risk of carbon loss due to increasing wildfire and drought severity. And here we characterize ecosystem stability as both resilience and temporal stability. So resilience is the speed of functional recovery following perturbation, and temporal stability is the persistence over time of ecosystem function. And we use 12 variables representing forest structure to evaluate whether structure differed significantly between management types, and whether specific structural features could be targeted with management to enhance stability. And resilience is calculated as the regression slope of relative function over time, and temporal stability is the inverse of the coefficient of variation over some time step. And we evaluated this functional resilience and temporal stability of three key ecosystem variables: evapotranspiration, or ET, gross primary productivity, or GPP, and ecosystem respiration, or RECO. And collectively, these variables represent salient pathways that define land-atmosphere interactions. So the uptake of atmospheric carbon by photosynthesis on the land surface, or the release of terrestrial carbon through respiration, or the exchange of water between the land surface and the atmosphere. And these stability metrics were calculated using 80 years of model data from the same set of simulations. And we next use generalized additive modeling to figure out whether these dimensions of stability were more impacted by management type or by climate, and interactive effects were also included as predictors. And Pearson correlation was then used to determine the directionality and strength of relationships between stability metrics and different structural variables. So what we found was that management primarily shapes functional resilience. So resilience is a dimensionless quantity. It can either be positive, negative, or zero. And a zero value indicates no recovery of function following perturbation. A positive value indicates more rapid recovery following perturbation than the control scenario. And a negative value indicates lower resilience than the control. So in the figure here, columns represent our ecosystem functional variables. The top row is the Great Lakes, the bottom row is the southeast. Data points are colored by management type, and point shape corresponds to climate change scenario. So we found that average resilience differed significantly between regions, and resilience decreased from the start to the end of the century. On average across all 3 dimensions in the Great Lakes, but temporal trends in resilience varied more by management type in the southeast. And on average, by the second half of the century, resilience was higher in the southeast than in the Great Lakes region. And resilience differed significantly between all management types in the southeast, but in the Great Lakes region, differences were only significant for passive management. Ecological and production forestry basically had the same outcomes. And we saw that in the Great Lakes, passive management really enhanced functional resilience on average, whereas both ecological and production management tended to decrease resilience. Whereas in the southeast, ecological management really had the greatest positive impact on resilience, and all management types had a net positive effect on resilience under RCP 4.5, and most had a net positive effect under RCP 8.5. And ANOVA analysis showed that while RCP scenario was a significant predictor of resilience, functional resilience overall was really shaped primarily by management. But for our second dimension of stability, temporal stability, it was really driven by climate. So temporal stability is a dimensionless quantity that's inherently positive. So a larger value indicates lower fluctuations around the mean over time. And in the figure here, columns again correspond to these same functional variables. Our top row is resilience. Our bottom row is temporal stability. Points are colored by management type, point shape corresponds to region, and line style is RCP scenario. And we're visualizing the change over time here, so our axis is average for the start versus end of the century. And we saw that temporal stability differed significantly between RCP scenarios in both regions, but that these differences by management type were only significant between production and passive management in the southeast. There were no significant differences between management type in the Great Lakes region. And we saw that temporal stability overall was lower under RCP 8.5, our more extreme climate change scenario, for all functional variables in the Great Lakes. But in the southeast, temporal stability was higher under RCP 8.5 for ET and GPP. And ANOVA of a similar GAN predicting temporal stability showed that regional climate change impacts as well as regional interactions between management and climate change scenarios were more important drivers of temporal stability than just climate change scenario alone. And finally, we found that managing for structural complexity could potentially increase resistance or resilience to climate change. So most of our structural variables varied more across management types than by climate change scenario, with the exception of mortality and tree density. And this indicates a greater climate sensitivity of those 2 variables, and a particularly strong climate-driven mortality signal in the Great Lakes, where you had amplified mortality across pretty much all management types under the more extreme climate change scenario. And across all metrics of resilience, lower resilience meant higher mortality. So this figure here depicts correlations between our variables, and blue are positive correlations, red are negative correlations, and the strength of relationship is represented by the color intensity as well as circle size. So we found that regardless of climate change scenario, resilience was really promoted by higher variability in tree height and size, so higher complexity. And this suggests that managing to promote structural complexity could increase resilience in the face of climate change. And considering the positive effects of complexity on resource use efficiency and productivity that were highlighted earlier, this is really promising for forest management as a nature-based climate solution. Okay, so what did we learn and why was it cool? So through exploring these mechanistic relationships between structure and function across scales, we really highlighted that vertical heterogeneity metrics consistently provided the most useful information about resource use and productivity, and the persistent superior performance of our reduced SEM, where the relationship between complexity and productivity was mediated by resource use efficiency, indicates that the existence of these persistent mediation effects that are scale independent. And this suggests that the relationships that are outlined here could be scaled from the stand to the ecosystem level and potentially integrated as parameters and models that simulate light and water sensitive processes. So this means that we could improve the ability of these models to mimic true ecosystem responses to disturbance. And zooming out in scale for questions 2 and 3, our modeling design really facilitated a more comprehensive understanding of interactions between management and climate change, as previous studies have looked at the responsive forest dynamics to discrete management events, or across significantly shorter timescales, or within climatically similar regions, or with cycled single-year meteorology, or only like one GCM as a driver. So with this approach, we were able to show that management was the strongest driver of future variability at the regional scale, but when you zoom out to broader spatial scales, variability across climate gradients becomes more critical. We also showed that the impact of management on functional stability was regionally dependent. It varies by management type and intensity, and temporal stability was primarily driven by climate, while resilience was primarily driven by management. So by integrating these fine-scale mechanisms from question 1 with this broader look at broad-scale kind of patterns and processes from questions 2 and 3, this really helps us to improve the understanding of how forest function will change across scales. And we can improve understanding of how we might represent the impact of management on land-atmosphere interactions and ultimately reduce predictive uncertainty regarding the future of the terrestrial carbon cycle. So this really allowed us to also improve understanding of how management change will impact future stability and forest function, which is a key part of being able to design these effective climate mitigation strategies that are actually going to be durable in the face of climate change. So that is all I have. All this work was supported by these funders. Thank you to my wonderful supportive partner, friends, family, awesome advisor, Ankur, and the Man4 research team.
Do you have time for a few questions from the group at large, if there is any?
So I think you mentioned that you used dynamically downscale climate model runs. I was kind of wondering if that included things like derechos and thunderstorm, severe thunderstorm gusts and things, and the effect of that on the mortality of the forest as the climate changed and in the different regions, because that's one thing that's changing.
Yeah, definitely. So we use the downscaled output from GCMs to do this. So it went from like a daily resolution to I think 3 hourly. And so the impact of natural disturbances like the ones that you mentioned are definitely increasing with climate change severity and are very important when trying to understand some of these like disturbance responses. Here we were specifically more interested in kind of the management side of things. So how are our actions changing things and how can we adapt our actions to kind of improve outcomes? So we didn't explicitly look at the impact of specific natural disturbances like those.
Okay, thanks.
Yeah, and if you want to know, the downscaling work came from a former master's student in the lab. Basically, the idea was using real-time time series of local meteorology, comparing that to daily RCP GCM's output, and then preserving the covariance structure across that. So it would have some of the events, but it wouldn't necessarily capture, say, some of the extremes that might be coming out. That's an interesting direction too. Anything else?
There is one online.
Yeah, go for it.
Did complexity measurements include or control for amount of vegetation? That is, was complexity primarily the structure and heterogeneity, or did it also include the amount of vegetation? That was from Murphy.
It's my brother. It included, I mean, so we had things like leaf area index in there, so it does include the amount of vegetation as part of that. Yeah, and so looking at a variety of like 9 different sites that were really different in kind of both the structure as well as like how vegetation was distributed helped to get sort of a representative distribution of what that impact was.
Other questions from the public before we sequester with the committee? Well, if not, I do also want to acknowledge the committee, Jack Williams, Eric Marie Spiota, also Chris Bouchard, all here, first thing, great. So we will reconvene in about 10 minutes or so. But before we do that, let's give one more round of applause.